Alrighty guys, so the next algorithm we're going to take a look at is going to be our Dequeue algorithm. And this algorithm is going to be what we use when we want to get something out of the queue. And we're going to be interacting with just the front of our queue. So this is going to be pretty much the same as popping a node off of a stack. We're just going to have a little bit extra to deal with because we've got that back reference. But other than that, it's going to be pretty much the same. We're going to have similar performance characteristics as well. So what are we going to need to have when we do our Dequeue? So when we Dequeue, all that means is that we're just removing someone from the front of the queue. We're taking something off the front. So we're going to need to be able to update the front and the back reference. So we have to have both of those things in scope. Now we're going to start off, we're only going to dequeue something. We're only going to be able to remove something from the line from our queue if there's actually something in it, right? So let's check to make sure that there's actually something in it. So how can we test that? We're just going to check to see if the front reference is not equal to null. If it's not, then that means that we've got something in our queue and we can remove it. So let's talk about the different types of scenarios we're going to have. We're going to have either an empty queue, in which case both our front and our back, remember we defined an empty queue as being the front and the back references pointing to null. We could have a queue that has got just one node in it, in which case both the front and the back are referring to the same node. And we can have a multiple node queue. And for this example, for this discussion, it doesn't really matter what values are in these nodes because we're just going to remove them. Right? We're going to examine a peak algorithm here in a bit that we will use to see what's actually at the front of our queue. But for our Dequeue algorithm, we're just going to remove the first node in our list. Okay. So anyways, let's get back to this. If the front reference is not null. Now in the case of an empty queue, then that's going to be false. So we're not going to do anything. We're done. We're out. Okay. Otherwise, what we need to do is we need to update that front reference. And we're going to set it to just point to or refer to the next node in the queue, the next node in the list. So we can just do something like this. We can just say set front to front next. And that's literally it, what we're going to do with that. Now we're going to have a situation, well, what happens if we have our back reference, right? We're going to have to deal with that thing. So we'll add that here in just a second. Now let's take a look at this third scenario right here, right? So if we do Dequeue, then first thing we do is we check to see if the front is not null. In that case, it is not null. It's true because front is referring to first node, the front node. So then, since that's true, we'll kick down to the F, set to F next. So we're going to overwrite the contents of the F reference with the contents of the next reference in the node being referred to by our front reference. So that's going to change our picture to this. We're going to have that front reference referring to the next node in the queue. And since there's nothing referring to the first node, or what was the first node, then the garbage collector is going to come along and take care of it. It's going to remove it from memory. So far, so good. Now let's do it again. Let's trace through it again. So if we wanted to do a second Dequeue, is the front not null? True. So we set the front to front next, and then the garbage collector comes along, removes that node. Now, this is where things get a little bit more complicated. And we'll see why here in a second, right? Now we're in that second scenario here. And that is, we come along and we do another Dequeue. So what does our algorithm say? Well, if front is not null, that's true. Then set the front to front next. Well, what's in front next? Null, right? It's referring to null. So we overwrite the contents of our front reference with the contents of that next reference in the node that front was referred to. So we end up with a picture like this. Okay, but we're not done yet because notice how the back reference is still referring to a node. The garbage collector is not going to come along and free up that node because it still has a reference referring to it. So we've got to update this back reference to also refer to null. But we can't do that in every single situation, right? We could see from the previous two Dequeue operations, we didn't want the back reference to move at all. So we're only going to do it if front is referring to null. So we'll put another little if statement in here, and we'll say if the front is null, then we'll set the back reference to null. And if we do that, then in this situation, this scenario, that if statement is going to evaluate the true. So we're going to overwrite the contents of our back reference with null. And when we do that, there's no longer any references pointing to that node. So the garbage collector is now free to come along in and get rid of it. And we're left with an empty queue. We've dequeued everything. We've removed everything from the queue that exists. Now, if we were to attempt to do a dequeue again, we'd have our if statement, if f not null. Well, in this case, that's false. So all of those operations, all the rest of that stuff just gets skipped. So we can't accidentally try to access an invalid memory location. We're protected by that first if statement. So let's take a look at some analysis. So how, in the worst case, what's our big O going to be? Well, we know that we're going to always have to do this first operation here, right? So that's going to be one. We're always going to be testing that front reference. Okay, now, in the worst case, it's going to evaluate to true. So that's going to give us access to this stuff in here that we're going to have to evaluate. So if we get in here, we know we're going to do this. We know we're going to set f to f next. So that's another operation we're going to have. And then we're going to have to test if f is set to null. That's always going to happen. Okay, now in the worst case, where worst case is when you have to do as many operations as possible, this would evaluate the true, and we'd have to do one more operation here. Okay, so the worst case, as it turns out, is if our queue looks like this, and we do a dequeue, because then we're going to have to do all 4 of these operations. So that's going to be big O of 4, which is still pretty darn awesome, because that means it's a constant time algorithm, and that's going to become big O of 1. So constant time, which should be easy to see at this point, because you can tell that we didn't need to have any loops in this algorithm.